Hello again. We're on to chapter 11. This is the second chapter of the muscular system. And the last one was full of physiology, how muscles function, and the process of a muscle contraction. This one's kind of the opposite side of the spectrum, and that is it's just a tremendous amount of anatomy. It's a matter of organizing these muscles, putting them in your head based on where you find them. There is a tremendous amount of number of muscles, so that vast amount of information makes it difficult, but the actual understanding or remembering steps, not so much in this chapter. So first we'll talk about how muscles are named, and well, how they're organized, I guess, and that helps you understand a little bit about how they're named. We are just talking about the skeletal muscles here, and their organization, so how they lie on the body and how the fascicles get together. Now fascicles, we're still talking about fascicles that where the protein fibers are laid down in very parallel fashions with the sarcolemma, with the sarcomere being the contractile unit. But what happens is the fascicles themselves can get together in organized ways, and that affects the dimension of the movement, I guess, the power of the movement, speed, and also the range of the movement. Just a few reasons why that is affected. The classification can be parallel, convergent, pennant, circular, multipennant, fusiform, bipennant, unipennant, and I think I have included all of those. Some of those are bunched together. This picture didn't come from your textbook, but something very similar is in your textbook. Some of your book tends to piece some of them together, and we do go by your textbook always. So they're classified by the way the fascicles are organized and the relationship of the fascicles to tendons. So how they're attached to, how the connective tissue that surrounds the muscle itself attaches to the tendon, and then also how the tendon attaches to the bone. Four basic patterns again: parallel, convergent, pennant, and circular. I think, well, let me go back. Sorry, I didn't mean to go forward because I didn't know if I had another picture. So I do want to talk a little bit about the different types. With parallel, and you see parallel, that's the second on the left in the middle. The fibers are parallel to the long axis of the muscle, and like the biceps brachii. And that creates a fairly broad movement with regard to parallel. With convergent, you have broad muscle areas on the attachment site, like the aponeurosis, and fibers can pull in different directions depending on the situation. So depending on how they're stimulated, sorry, not the situation. So fibers can pull in multiple directions. Think of convergent, think of that pectoralis major. And if the pectoralis major basically takes your arm toward the midline, but you can come toward the midline in varying angles. So your convergent manages to do that. And that's what they mean about how the muscle of the fascicles relate to the tendons. You can see with that pectoralis major, the fascicles start off on a wide, I guess, height at the sternal part, at the sternal aspect of the pectoralis major, and then converge into a point on the tendon. Then the pennant, which we have 1, 2, 3 type of pennant muscles. We have unipennant, bipennant, and multipennate, they form an angle with the tendon. So they form an angle in relationship to the tendon. Don't move as far as parallel. Parallel tend to have a little bit broader movement, do contain more myofibrils, and can develop more tension so that they can contract in a stronger way, I guess you might say, than the parallel fibers. And the uni, bi, and multi are based on how many, what branches, how many branches. Circular, and that is like the sphincters, open and close the guarding of the body, the sphincter. You can think of your orbicularis oris, like your mouth. Not so much, they're not so much the muscles that cause your jaw to open and close, so that, but more what they say in lab, the kissing muscles. Or they actually say that in lecture. I'm saying it now too, so you say it in lecture. So it's a circular muscle that closes an opening, and you have sphincters all over your body, as well as you have sphincters. I mean, you have sphincters as gross anatomy wise as your mouth, but also microanatomy wise as closing off certain capillary beds. So guarding entrances, and also creating boundaries, I guess you might say, or creating when I say creating temporary boundaries. All right. Then the next thing, and shoot, I thought for sure I didn't have anything cut off. What it says at the top is mechanically each bone is a lever. So mechanically each bone is a lever. And so, and our definition here of a lever is a rigid moving structure. And then with that, the joint would be a fulcrum, which is the fixed point. So the lever is the bone, the fulcrum is the joint, and muscles are the applied force. So AF, and that applied force is required to overcome a load. So the muscles are the applied force. And then the function of a lever of the bone is to change the direction of the applied force, also distance and speed of movement of the muscle, and then affect the amount of strength the muscle needs. So the amount of applied force needed is facilitated by that lever. There basically are three classes of levers that we find in the body, and that is based on the relationship of applied force, fulcrum, and resistance. So first class, you see here, is like a seesaw. The center is the fulcrum, and that fulcrum is between the applied force and the resistance. So the fulcrum is between the applied force and the resistance in first class. Second class is like a wheelbarrow. And with that, you have the center of resistance between the applied force and the fulcrum. So the fulcrum is the wheel, and the resistance is the junk you got in your wheelbarrow, and then the applied force is there. You can see the gentleman holding the handles of the wheelbarrow. And that's a second class lever. A third class lever is most common in the body, and what you have is the applied force is between the resistance and the fulcrum. So you have W as the resistance here. The lady's got something in her shovel. The fulcrum is her other hand, and then the hand that's doing the lifting is where you have P there. And then you have an image underneath there with the third class lever. So it's just a matter of that relationship of resistance, force, and fulcrum in each of those. And remember, the third class is the most common that we find in the body. And then the next concept with regard to muscles is every skeletal muscle is going to have two forms of attachment. One fixed point where you have very little movement is the origin, and one moving point, which is the insertion. The reason I say about that origin you have very little movement, because if you had no movement, that would actually hurt the muscle. So you do have some give there, so you can think of it that way. But depending on where you are in your level of learning in terms of anatomy, origins are presented as having no movement, but that doesn't even make sense. And I think probably most of you would go, well, that doesn't make sense, because you want to have a little bit of give there. And so the origin is usually proximal to the insertion, proximal to the insertion, but insertions always move toward origins. Or I guess I should never say always, because as soon as you say always in the body, you find an exception. But generally, insertions move towards the origin. And movement or action is made by the muscles contracting and actually pulling the insertion towards the origin. And movements are described in terms of bones, joints, or regions. So you kind of defined actions or movements in terms of bones, joints, or regions. Muscles don't work in a vacuum, they work together. They work in groups generally. We even think of it as large muscle groups or the more finite muscle groups. And sometimes large and small work together, but generally when we start learning about muscles, all of these skeletal muscles, we think of at least there being a primary mover and then being an agonist. So antagonist and an agonist. I kind of like to use the word primary mover and antagonist because it keeps them separate. But so you have the prime mover and then the muscle that's going to oppose the prime mover. You also have muscles that are going to help or facilitate the movement. So the prime mover, the agonist, is going to produce the particular movement. So in the prime mover, the insertion is going to move toward the origin. And what we have here in the first picture is the bicep contracting. The bicep is the prime mover. Bicep, it has two heads on the upper arm. And with that movement, which is flexion, you have the triceps being the antagonist, and it actually is relaxing. So it actually is maybe doing the opposite action when you think of the fascicles, when the bicep is the prime mover. And then when that bicep is done with its job and you want to extend the arm, then the bicep becomes the antagonist and the tricep becomes the agonist. And so this goes on and on and on throughout the entire body, where with most of the skeletal muscles you have this pairing, as well as you have synergists. And depending on the unique property of the muscle that unique action that you're doing with the muscle, any muscle can be a synergist. Any muscle can be a helper or smaller muscle that assists. And it doesn't always have to even be the smaller muscle assisting. It can be something that's of equal size that actually stabilizes the joint or stabilizes the movement. And understand that these roles change constantly. So just because a muscle is a synergist in one movement doesn't make it a synergist in the next. And if it's a synergist in one movement, it can actually be a prime mover in the next movement. We will pick this up on the next lecture.